Next problem I want to look at would be problem number 52. If I'd like to take square root of 3 minus I raised to the 6th power. Again, one option is to multiply this by itself 6 times. And FOIL all of that. Or I could work this out and transform this into complex using Euler's formula. And if I move radical 3 to the right and 1 down, R would be, which is the modulus of Z, R equals a 2. And the reference angle, meaning you ignore the plus or minus, you would say tan of theta is 1 over radical 3. That has a reference angle of pi over 6. And if I want to run pi over 6 into the 4th quadrant, that's e to the 11 pi over 6 I. And this is 2 to the 6, and if I multiply those, that's 11 pi I. That is 2 to the 6 times the cosine of 11 pi plus cosine of 11 pi plus I the sine of 11 pi. And identical to the previous problem, I know where 11 pi is. That's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. All the odd multiples of pi are right there, so this is negative 1, 0. And this turns out to be negative 2 to the 6th power, or negative 64. Now, last portion of this lesson deal with a very important application. The fundamental theorem of algebra in college algebra stated that if you allow complex roots, then any polynomial of power n will be able to, you will be able to write it as the multiple of n factors, meaning the number of solutions will match the power. When they say here the complex fourth roots of square root of 3 minus I, what they really mean, they mean that z to the 4th equaled square root of 3 minus I. Find z. You should have 4 solutions. Complex 4 roots, that means 4 solutions. Complex 6 roots, 6 solutions. This is something that will come up in differential equations, math 55. The same idea, we just did that problem, so let's get that out of the way. That is, we just did radical 3 and negative 1. Oops, negative 1 is smaller than radical 3, right? So let's say right there. So we already know from the previous problem that this is a 2 and this is 11 pi over 6. So this is actually 2e to the 11 pi over 6i. Now, if I take the fourth root of both sides, I'll get z to equal the 4th root of 2 times e, and do remember that the nth root of a is a to the 1 over m, or the nth root of a to the m is a to the m over m. So I'm going to write this as e to the 11 pi over 6i, and I'm going to raise that to the 1/4 power, and z is going to equal 4 the square root of 2 times e, and if I multiply those out, that is 11 pi divided by 6 plus 2 pi k I all raised to the 4th power, 1/4 power, and z will equal 4 the square root of 2 times e, and if I multiply those, that's 11 pi 11 pi over 24 plus 2 pi over 4k I. And if I want the four solutions, z equal, for k equals 0, I'll get z equal the fourth root of 2. And it says leave the argument in polar form, which is good. Oh, and it says degree. I'm sorry, I forgot about that. So this is pi over 6, that's 30 degrees. This is actually 330 degrees. So you could convert to degrees, that's not a problem. Or you could leave them ready, it's not that big of a deal. The next problem I'll do with degrees. So this is going to be E. If I put k equals 0, I will get 11 pi over 24i. That's the first solution. If you let k equal 1, z will equal the fourth root of 2e. If I take 11 pi over 24 and add 2 pi over 4 to it, all over 24 times 6 times 6, that's 23 pi over 24i. If I let k equal 2, I'll get z to equal 4 the square root of 2. If I put a 2 right there for k, then I went from 11 pi over 24 to 23, add 12, add another 12, that's 35 pi over 24i. And if I let k equal 4, I'll get k equal 3, I'll get the last solution, and that would be z equal the fourth root of 2e, another 12, that's 47 pi over 24i. Keep in mind, this is still less than 2 pi. If I let k equal 4, I'll repeat this. So here they are. I am going to do another example of those. Those are called roots of unity. The applications of those are tremendous in engineering. For now, you're learning how to do those. They're not telling you why you're going to use them for. Let's look at number 62. And again, this is something that you need later on. If I look at the complex fifth roots, which means I need 5 solutions to this. Anytime I need more than one solution, I add 2 pi k. And keep in mind, you could add 2 pi k anytime you want. That doesn't change any value in complex numbers because they're really polar. So here I'm imagining this says z to the fifth roots equal negative I. Well, I know where negative I is. Negative I is actually right there. So I know that r equals 1, and I know that theta equal 180 degrees. So I could write this as 1e to the 180 degrees I. Now, since I'm going to take the fifth root of both sides, and I want more than one solution, I'm going to say that's 180 degrees plus 360 degrees I. And I'm going to do the same trick. I'm going to write this as e to the 180 degrees plus 360 degrees I, all raised to the 1/5 power. And that will turn out to be e to the 180 degrees divided by 5 plus 360 degrees I over 5. And z will equal, now normally they call this z sub k. You don't have to worry about that now. That's going to be e to the 36 degrees plus 72 degrees times I. And I could start with the traditional. I'm going to let k equal 0, k equal 1, k equal 2, k equal 3, k equal 4. And if I let k equal 5, I'll check what happens. So here, z sub 0, that's what they call it. You could just say z if you want. That's e to the 36 degrees I. They said leave it in polar form. This is polar form. The book will write cosine of 36 degrees plus I, the sine of 36 degrees. That's the same thing. equal 1, I'll get z sub 1 to equal e to the 36 plus 72. What is that? 108. And z sub 2 will be e another 72, that is 10, that's 180. Z sub 3, another 72, that's 215, 252i. Z sub 4, another 72, that is 4, that is 12, 324 degrees I, so those are 5 solutions. And what happened if I let z equal 5? I'll get z sub 5 to equal e to the another 72, that is 396 degrees I, and if I take 396 degrees, subtract 360 degrees, I'll notice that this is 36 degrees. You start repeating yourself. Those are called roots of unity, and later on, those are called eigenvectors and eigenvalues. No need to worry about that. I'm going to list the homework out. There's the homework, and that concludes this section. And I'm going to upload this in the PDF form as well.